Hi, in this video, I'll show you how to use the comparison test, also known as the direct comparison test, to check for the convergence or divergence of an infinite series. Let's say that we're given the series sum of n from 0 to infinity of a sub n. In talking about the comparison test, we can assume that the terms of the series are positive. Well, naturally, your first question is, well, what if it's not? What do we do if the terms are not positive? Well, there are two common situations when the terms are not all positive. The first situation is if the terms are all negative. Well, if they're all negative, think of it as some negative a sub n, then we can factor this outside. And now we have what's left are all the positive terms. So that's one situation and easily taken care of. The second situation is a little bit more complicated. It's a situation where the first term could be positive, but the second term is going to be negative, and then the third term, the A2 term is going to be positive again, and then A3 is negative, A4 is positive, etc. When that happens, we say that the series is alternating. It's an alternating series, and the alternating series have their own tests of convergence and divergence. So we don't have to worry about it. And then, of course, there are other situations, but these are the two most common situations, and we don't need to worry about them. Therefore, for purposes of this video, it's perfectly okay to assume that the terms of the series are positive. And in fact, we're only going to be dealing with series where all the terms are positive when we're talking about the comparison test. All right, so this is how the comparison test works. The idea is to compare our terms a sub n with other series, some other b sub n that are known to be either convergent or divergent. And then based on that, we can conclude about A. Let's do the divergent situation first. Let's say that there is a series sum from 0 to infinity of d sub n. This series is known to diverge, and again, we're assuming the terms of the series are positive. What happens when a series where the terms are positive diverge? Well, a series that's all positive means when you add on another term, it keeps increasing, right? It never goes back down. So to diverge means it increasing so much it goes to infinity. That's the divergent series. So this is our series d sub n. Well, then we take our series a sub n. At the beginning, it could do whatever. It could be smaller than d or larger than d, whatever. But we know that at the beginning, as soon as, even if you are talking about tens of thousands of terms, if you add tens of thousands of terms together, it's still going to be finite. So the beginning of series is never an issue. The issue is always at the tail end of the series. At the tail end, if we know that our a sub n is bigger than d sub n, and d already goes to infinity, then the sum of a sub n for sure will have to go to infinity because it will have to be bigger. So if this happens, then we know that the sum of a sub n also diverges. So the first rule is that if you compare and you find out that your series is larger than a divergent series, then your series also diverges. That's rule number one. Now let's take a second situation. Let's say there's a known series C sub n where it is known that the sum sub C sub n converges. And again, we're also assuming that C sub n are positive. Then what does it mean for C sub n to be convergent? Well, that means you start out with some C naught value, the first value, and you add on under the C term. And since C is positive, you'll increase by a little bit. And you add on another C, it increases by a little more. But we're assuming that C sub n converges. That means it cannot go all the way to infinity. It will have to hit a ceiling somewhere. It will have to hit some sort of horizontal asymptote on top. So that means eventually you'll have to taper off like that. That's what it means for a sum of C sub n to converge. Well, what about our sum A sub n? Again, we don't care about the beginning. The beginning could be whatever. But after a while, if we know for sure that our A sub n is going to be less than C sub n, then that means if we add on all the C sub n, there's no way it can exceed the C curve. It cannot punch above the C curve. Well, if it's not going to punch above the C curve and it keeps increasing, then that means eventually you'll hit some sort of ceiling. Again, it could be the same ceiling as the C or a lower ceiling, but it has to hit some ceiling because there's no way it can punch through to infinity. So a situation where A sub n is less than C sub n, then that means A sub n, the sum of A sub n, converges. So our rule number two is if it's smaller than convergent, it converges. That's our second rule. What about all the other situations? What about the situation where it's larger than something convergent? Or if it's smaller than something divergent? Well, let's take a convergent series. Let's take a C sub n that converges. So it hits some sort of ceiling. Well, if our A sub n is larger than C sub n, then it could be convergent. It could hit some ceiling, just, a higher ceiling than C sub n. Or it could go all the way to infinity. Who knows? Who knows what's going to do? So this situation is like, yeah, if your series is larger than a convergent series, we have no idea what's going to happen. And likewise, if you have a divergent series and our A sub n is smaller than the divergent series, or then it's down here somewhere, but we don't know what it's doing. It could be hitting a ceiling under the n, or it could go to infinity. It goes to infinity below the n, but it's still infinity regardless. Yeah, this is another situation where we have no idea what's going on. So larger than convergent, no idea. Smaller than divergent, no idea. We do want one of these two situations. Number one, either we want our series to be larger than a known divergent series, in which case our series diverges. Or we want our series to be smaller than a known convergent series, in which case our series converges. The other situations, we cannot draw a conclusion, so we cannot use the comparison test. At this time, you can tell that that means we need to know certain series that are either for sure divergent or for sure convergent. We need to know one or the other. Two very common series that we use all the time in comparison tests are the geometric series and the p-series. The geometric series comes in the form of some constant r to the power n, or sometimes it's written as n minus 1, depending on the book. The geometric series converges if the base is less than 1, and it diverges if the base is greater than or equal to 1. There's one way to remember the rules of geometric series easily. It's like this. Think of this prototype. Sum of 2 to the nth. Well, 2 to the nth is 2, 4, 8, 16. It gets bigger and bigger, so if you keep adding that, for sure it will diverge. Well, that is because the base is too big. So when the base is too big, it diverges. Whereas when the base is less than 1, you can think of numbers like 1/2. So you have this series that has a known sum of whatever the first term is divided by 1 minus r. But you really don't need to memorize this for purposes of figuring out convergent and divergent. Just have to remember it does converge. That's a geometric series. The p series is the sum of 1 over n to the power p, and it converges when p is greater than 1, and it diverges for p is less than or equal to 1. Well, between 0 and 1. When p is equal to 1, then we have 1 over n like this, and this is called the harmonic series. The harmonic series is a special case of the p series, and it diverges. Well, the harmonic series happens when p is equal to 1, and that is right at the borderline between divergent and convergent. And at that borderline, it falls on the divergent side. So the harmonic series within the world of p series is even more important than the rest of them because it really helps prove that things are divergent. Now, I've seen people getting confused between the geometric series and the p series, and here's the difference. The difference is where n is. If n is in the exponent of the power, it's a geometric series. If n is in the base of the power, it's a p series. So that's the major difference between the two. All right, so you're going to be using these known convergent series and known divergent series to do your comparison tests. So now I'm going to go through some examples. Let's take this series, sum for n from 0 to infinity of n plus 1 over n squared of n. I want to compare this with something, but how do I know what to compare it with? At this point, I suggest you use the skill you learn in doing things like n behavior in algebra or limits in Calc 1. Using that skill, I look at this and I say when n is large, then n plus 1 is basically just n. The numerator is basically just n. And the denominator is n squared n, then find n squared n. And these cancel. And so this is basically 1 over square root of n. What do I know about this 1 over square root of n? This is the same as 1 over n to the power 1/2. This is a p series where p is less than 1. This thing diverges. So I want to prove that my series diverges by comparing it with this series. So let's go ahead and do that. I want this. I want my series to be greater than or equal to 1 over square root of n. Well, remember how I got to 1 over square root of n? I got there by like omitting this plus 1, right? So I'm going to do that again. N plus 1 over n squared of n. What happens if I omit the plus 1? Then the number gets smaller, right? When the numerator gets smaller, then the whole fraction gets smaller. This new fraction is smaller than the old fraction. The old fraction is larger than the new fraction. And then this one simplifies to 1 over square root of n. And this series diverges. So I'm done. Since summation of is a p series with p equals 1/2. And 1/2 is less than 1. That means it's divergent. Our terms are larger. Therefore, it's also divergent. And that's how we know that this series, this given series, diverges. Before I move on, let's go back and see what I did. Number one is I use the end behavior or limit scales to find the series I want. That's the series I want to compare with. Well, number two is I also, based on that, I figure out that the inequality I'm looking for. I knew that this inequality is what I want. I want this inequality. And so that leads me to number three. I do my algebra in that direction. I do my algebra with that strategy in mind. I do my algebra with the strategy of getting my series a sub n to be greater than something, not less than. If my a sub n ends up to being less than something else, I'm not interested because I'm looking for greater. I do my algebra with that goal. So the algebra that's being done here with like skipping the plus 1 to get the greater than, it was not random. It was with intention. Now let's take this new example. Sum for n from 0 to infinity of 3 to the nth minus 1 divided by 5 to the nth plus 1. So step one is the same. I'm going to use my end behavior or limit skills to figure out what should I compare this series with. Well, when n is very large, then add 1 or subtracting 1 from it makes 0 difference. So this is roughly the same as 3 to the nth divided by 5 to the nth. Well, I think of the series that I know that I should compare with. There's a p series. It has n in the base. This one has n in the exponent. The other series is a geometric series. It has R2. This one has two bases. There's a 3 in the numerator, and there's a 5 in the denominator. I need to make it into just one. And I know how to do this, because 3 to the nth over 5 to the nth is the same as 3/5 to the power n. Okay, so now it looks like a geometric series. What kind of geometric series? Is a geometric series with R equals 3/5, which is less than 1. And that is convergent. So I suspect that my series is convergent. And I want it to be less than or equal to this series. So that's the goal. So at the end of step one, I know that the comparison I want is 3/5 to the power n. And because this is convergent, I want to prove to be less than convergent, right? I want one of two things, larger than divergent or less than convergent. I don't want anything else in between. So what I want is my series, my a sub n, to be less than or equal to 3/5 to the n. So I'm going to do my algebra in that direction. So step 3, I'm going to do algebra in that direction with that goal or at that strategy. I want this one to be less than or equal to something. What can I do? So from here to here, I want to go bigger. What can I do with a fraction to make it go bigger? Well, I can make the numerator bigger by not subtracting 1 from it. And I can make it bigger again by making the denominator smaller. Remember, when the denominator gets smaller, the whole fraction gets bigger. 1/5 is smaller than 1/4. So I can make it bigger again. It really is strictly less than, but it really doesn't matter that much. If you happen to write less than or equal to, it's still a true statement, so it's still okay. And then this is 3/5 to the nth. Since a series of 3/5 to the nth is a convergent geometric series, and our a sub n is less than 3/5 to the nth, that means our sum a sub n converges, where a sub n is this big term. So that's my whole solution. And this is my strategy. So let's summarize the strategy again in one screen. Given a series a sub n, you use your n behavior or limit skills to simplify a sub n to some known convergent or divergent series. And let's call that other series b sub n. Then number 2 is decide what we want. Do we want a sub n to be greater than or equal to the new series, or do we want it to be less than or equal to? And remember that we only want one of two things. We only want our series to be either larger than a divergent series, in which case it diverges, or smaller than a convergent series, in which case it got capped with a ceiling and it will converge. We don't want any other combination. And number 3 is we're going to do algebra on the a sub n to convert it to the b sub n with that inequality in mind. If we decide we want a less than symbol, then make sure you always do it in such a way that it's this one is less than that one, less than that one. Don't go in the wrong direction. Now, the problem is sometimes it doesn't work. Then what happens when it doesn't work? Now comes step 4, which I will write down, but I won't do in this video, and it's this. When that algebra doesn't quite work, switch to the limit comparison test. In fact, that's pretty much the purpose of limit comparison tests, to free you from the strict inequality situation of the direct comparison test. All right, but this video is about the direct comparison test, so I'm going to stop here. And I hope it's been helpful. Any questions, leave it in the comments section below. Like, share, and subscribe for more contents. And thanks for watching. Bye.